In this video, we're going to set up a very simple system where we can specify an object for our audience to look at. We're also going to be creating an offset parameter so that we can adjust how they're looking at the particular object, just in case it looks as if, as far as the viewport is concerned, our spheres are not looking at the object, or not looking right at the object. Now, Steve's going to do a little whiteboarding in this video, so this is going to be fantastic. What you got, Steve?
Cool, so let's jump over to our whiteboard, and I'm going to bring up a new sheet. So, well, what's the objective? We've got our spheres, they're being copied 2 points, and we need to basically rotate our sphere so that it's looking in a different position. And how are we going to approach doing this? Well, we're going to do it on a sphere-by-sphere basis, so I'm feeling some stamping coming into the equation. So let's just deal with a single case, and that is we know we have a point somewhere in 3D space as the graphics tablet catches up with me. There we go. And we're going to have a sphere copied to this point, and then we're going to create a way of specifying an object. And that object plus our offset is going to give us some location in 3D space that we want to look at. So let's say this is where we want to look at, and we need to basically rotate our sphere such that this guy looks at this guy. Well, we could do a huge amount of maths, work out the difference in positions and vectors, and work out the rotations, but Houdini provides a couple of really nice expressions that allow us to basically do this automatically. So, cool. So basically, if we have point A and point B, there is an expression function called mLookAt that will allow us to basically calculate a matrix that sets up the transformations required for point A to be rotated such that it looks at point B. So the expression function is mLookAt, and it takes in a point, so that would be point A, and a second point, point B. It's going to calculate a matrix. Now, for those of you who are familiar with matrix mathematics and the way matrices can be used for transformations, you'll know that a single matrix can contain a number of transformations. And in this case, it contains 3 transformations that are incredibly important for us: rotate X, rotate Y, and rotate Z. We've got a matrix, and we can't directly apply that matrix to our rotation channels because it's not a single float value, it's a matrix containing a number of values. So we need a way of jumping inside this matrix and grabbing that rotation information and pulling it out so that we can then apply it to our sphere and rotate our sphere to look at this point. So how are we going to do that? Well, Houdini provides another expression function that allows us to take a matrix. Well, this guy returns a matrix right here. So we can take the matrix returned by this guy and tell Houdini which component are we interested in pulling out, and that will then return the floating point value. So what's this expression? This expression is explode matrix. And it takes in a matrix, so it's going to take in this guy as our first input. And it then takes in a couple of pieces of information that specify the order of transformations and the order of basically axes that we're dealing with. So we're going to use the defaults, which are rotate, scale, translate, and then X, Y, Z. This becomes a lot more important when you're dealing with wanting to take out rotation information and translation information, and which order you're going to be taking these out and reapplying. We're just dealing with rotation, so we're going to use the defaults as explained in the help file of rotate, scale, and translate, and then X, Y, and Z. It's the final parameter that's the really important parameter, because this is where we get to specify which piece of information are we interested in. So let's say we're interested in rotate X. Rx is the string that we'd use to grab rotate X. Well, what exactly does this mean? It means that mLookAt is going to calculate a matrix that makes this point look at this point, and for one point to look at another point, it has to be a series of rotations so that we're going to reorient ourselves. And with those series of rotations, explode matrix is going to jump in and pull out solely the rotate X rotation. Now, what if we were to then jump in and say, okay, we've got rotate X, I now want to get rotate Y. We then pull out the rotate Y equation. And finally, we could jump in and grab rotate Z, pulling out all 3 pieces of rotation information. So we'd end up with a rotate X, a rotate Y, and a rotate Z, all three of these together, we can combine to get the rotation to take point A from its current position and rotate to look at point B. So how are we going to apply these? Well, we've seen that we've got, let's scroll down to grab some whiteboard. We've seen that we've got our sphere, and our sphere is running into a twist, so sphere, and our twist for our animation. And this guy is feeding down, I'm going to leave a space, feeding down into, that's really anything but straight.
No, that's alright.
Let's draw this again. If you can be picky, I can be picky.
Fair enough.
Feeding into our copy, and we've got our points coming from our distribution network into the second input. So what if we were, on this copy, to calculate this rotation information? Because on this copy we have access to the point that we're being copied to, and we have access to basically the position we want to look at. This is the point we're being copied to. This is the position we want to look at. So we have all the information we need down on our copy to say, okay, the point we're being currently copied to, well, we know that that exists at $tx, $ty, and $tz. And we know that the point that we want to look at is the object that we're specifying plus the offset that we're going to specify. So with those two pieces of information, we could calculate rotate x, rotate y, and rotate z using the two expression functions we just discussed. And we could stamp each of these back as a separate parameter from our copy, stamp them back to a transform SOP, and use these on the rotate x, rotate y, and rotate z parameters of the transform SOP. So our sphere comes in, and based on the position it's being copied to, he's going to get rotated before he's copied, such that he's going to look at our basically our specified position in space. So for each of the points that we get copied to, that rotation is going to be different, so that our entire audience, based on where it's sat at, is going to look at that position in space. So now let's take a closer look at how we're going to use mLookAt, because currently we've just said point A and point B. Well, how are we going to get these 2 points? Well, point A is simple. We've seen that it's constructed from $tx, $ty, $tz, but mLookAt needs it as a single parameter. It needs it as a vector 3, so we can use the vector 3 expression. So we have a vector passing in 3 floating parameters. So we say, okay, I want a vector from 3 float parameters, $tx being the x component, $ty being the y component, $tz being the z component, and this can become A. So we've now constructed a vector as opposed to having our 3 single floats, and that's going to give us the point we're being copied to. But what point do we want to look at? We want to look at B, and we discussed that B is both a specified object. In this case, we're going to specify a null object, which is just a location in space. So we're going to have our drop down, and we're going to specify some object. Let's just say it's obj/null1. We want to grab this object's transformation information, but also take into account our offset parameter that lets us say, okay, take that and add 10 to it in x, or subtract 5 from it in y. So how are we going to do that? Well, let's look at the case for just one component, because if we can work out one component, we can work out y and z as well. So for x, how are we going to work this out? Well, we need to grab our translate x of this guy, and we've seen this before when we were dealing with making one object sit on another object. We can use the channel string expression to grab the text that is in here. So we can say, okay, jump up and grab the text from whatever we call this parameter. And I'm going to call this parameter audience lookat. So let's jump up and grab the text from here as a string and concatenate to the end of that string /tx. So we grab the translate x parameter. But we need to grab this as a parameter, so we need to use this as the argument to the channel expression. So that's going to give us the tx information of this particular object, and we can take that and add to that our parameter we've created for our offset in x. So in this case, I'm just going to abbreviate this to offx, but this will actually be a vector parameter that has an x, y, and z component, which the parameter is going to be called look at offset. So that's going to have a look at offset x, y, and z component. So this here between these two quotes, so all of this, including the plus sign, is going to give us the x component of point B. So if we were to take all of this and plug it into another vector3 expression as our x component, and then do the same but for ty and y, and for tz and offset z into our y and z components of our second vector3, we've now completed our m look at expression. This will return a matrix that makes this guy look at this guy, which we can then use explode matrix to pull out our rotation data, so rx, ry, and rz, such that down on the copy we can stamp rotate x, rotate y, and rotate z back to our transform, rotate our sphere before it's copied, and our sphere will look at our point in space.
Excellent.
Cool, so
let's do it.
Sweet. Alright, so now we're over in Houdini. The first step's going to be to create two new parameters on our asset. The first to specify the object we want to look at. The second to specify an offset from that object.
Okay.
So I'm going to right click on our bleachers asset, come down to type properties, and underneath inside our audience folder I'm going to create an operator path and a float vector3. So the operator path is going to be for our object that we wish to look at, and that's going to be named aud look at, for audience look at. And we're going to set the op filter to be any object, so we can grab a geometry node if we want, or we can grab a null at object level if we want.
We can look at a camera, we can look at lights.
Anything that has transformation information.
Anything that's an object.
Fantastic. And our second parameter is going to be a float vector3, and this is going to be for our offset. So I'm going to name this look at offset. Look at offset. I'm going to leave everything else as default parameters. So if we accept this, we can now jump up 2 levels to object level, and I'm going to create a null that we're going to use, at least for now, for the object we wish to look at.
Okay.
So I'm going to push tab to bring up the tab menu and create a null, enter to accept that, enter to drop this into our network, and I'm going to rename this to audience look at. We can then jump inside our bleachers. I'm going to double click on them, and from our parameters we can specify our audience look at object as well as our offset. So for the audience look at, I'm going to bring up the browser, grab our null, and make sure that I'm exporting an absolute path as opposed to a relative path. So we can see we've got /obj/audience look at, and for now I'm going to leave the offset at 0, 0, 0. Now if we jump back up to object level, we can see that our null is positioned at 0, 0, 0 as well.
So if you back away a little bit, show them. There you go. So that you can see the audience would be looking down at that.
So yeah, we'll know if this is working if our audience looks down at the origin, and then we should be able to come up here, move our null around, and change our offsets and see the effect that that has on the audience.
Spin just a second. Go ahead and hide out our
Everything
character.
else, yeah.
Everything else.
So let's hide our floor, let's hide our pool, let's hide the stage, let's hide the character, and let's hide the ladder. So all we're dealing with is our bleachers and our null.
Excellent.
Fantastic. So I'm going to jump inside our bleachers by double clicking, jump inside the asset by double clicking, and I'm going to find our copy audience copy salt. So on this copy salt we have access to all the information that we saw we needed. If we jump back over to the whiteboard, we have access to our position for our point that we're copying to, and we also have access, because of the fact that it's up on our digital asset, to our object and the offset that we want to look at. So we're going to stamp on a point-by-point basis the rotate X, rotate Y, and rotate Z information that we need to then send back up to a transform that we're going to create. Now the expression is going to be fairly lengthy, but we only really need to create it the once, because once we have the expression for rotate X, all we need to do is change out which component we want to pull out of that matrix for rotate Y and rotate Z. So let's create rotate X. So on the copy audience copy, up under the stamp tab, I'm going to create a third stamped parameter, which I'm going to call rotate X. And rotate X, I'm going to start by building just the mLookAt expression. Once we have that in place, I'll then wrap the explode matrix expression around it so that we can put out just one component of information. So the mLookAt, as we can see, needs 2 vectors, the position we're at and the position we want to look at. And we know the position we're at is $tx, $ty, and $tz, but that's 3 floats that we need to create as a vector. So we've seen we can take 3 floats and create it into a vector by using the vector3 expression. And this takes in 3 floats, so the first will be $tx, the second will be $ty, and the third will be $TZ. So that's for our first vector. Our second vector needs to take basically our target object, translate x, and add it to the offset in x. So to do that, we're going to create another vector, and we need to create the x, y, and z components of this vector. For the x component, let's take the channel, which is going to be our audience lookup, so ord lookup plus /tx. So we've concatenated the two strings together, and now we're referencing that as a channel, and that should be channel string since we want to grab the string information, plus tx, and then grab the overall channel. So that's how I translate x information from the null object currently. And let's add to that our offset in x, which is our lookat offset x. So that's our x component. We're going to have the exact same thing for our y and z, obviously replacing tx with ty, tz, and offset x with y and z. So I'm going to grab all of this, and if we highlight something by left-clicking and dragging, we can then middle-click to paste a copy of that. So I'm going to middle-click here to paste a copy, and middle-click here to paste a copy. So let's insert the comma in between. That's our x component. This is our y component up until here.
Yep.
And then this is going to be our z component. And we do want to make sure that we get rid of that final comma and close off our vector 3, that's the second argument to mlookat, and close off the mlookat expression itself. So now we've got our x component. We need to make sure that this is our y component, so tx needs to become ty, and offset x needs to become offset y. And finally, for our z component, we want tz and offset z. So you can see it's fairly lengthy, but it's a really simple expression. We're saying take our current position and generate the matrix required to look at our object we specified plus that offset. And we've seen this over on the whiteboard. So now that we have a matrix coming back, we can use explode matrix to pull out individual components of information from this matrix. So let's use the explode matrix function, passing in mlookat as our matrix that we want to take in. We want to take our translate, rotate, scale as the which order of operations we want to do, and we're going to use rotate, scale, and then translate. Then which components in terms of x, y, z, so x, y, z. And finally, and this is the most important parameter, and that is what component are we interested in here? And we're interested in rotate x currently, since we're generating the rotate x expression. And if we close off the parentheses, that'll close off the explode matrix expression. And that's everything for getting the rotate x information that we need. So if we accept this, and then we can right click and grab copy the parameter, and then I'm going to right click and paste copied expressions 2 further times, creating rotate y and rotate z. Where in rotate y, so I am bringing up the stamp parameter for rotate y, all we need to do is change the component we're interested in. We're now interested in the rotate y component. And in rotate z, I'm going to change the component we're interested in. We're now interested in the rotate z component. So now we have 3 stamp parameters for x, y, and z, and we can create a transform SOP. And I'm going to create this after we've applied our squash and stretch. So even if we're stretched out, we're going to rotate based after that point, rather than rotating and then still stretching in the y-axis. We want to do our deformation first. I'm going to wire this into a transform SOP. And I'm going to rename this to something like audience lookat xform. So we've got the 3 pieces of rotation information, x, y, and z, being stamped up from our copy. So now let's reference those in our rotate x, y, and z parameters on the transform SOP. So rotate x, we can grab stamp. It's going to be our copy audience. The parameter we stamped was rotate x, and let's default that out to 0. And we can already see that's had some effect. Our rotate y is going to be very similar. It's going to be a stamp. is going to be from our copy audience. The parameter was rotate Y, and let's default that to 0. And finally, our rotate Z is going to be a stamp. It's going to be from our copy audience. In this case, it's going to be rotate Z, and we'll default that to 0. Fantastic. So we can already see that our audience are indeed looking down at our origin. So we have 2 tests that we need to do. One will be moving that null to make sure our audience follow the null, and the other will be making sure that if we change our offsets that we see a difference. And with that, if those are successful, we'll have completed this video. So let's jump up a level and let's test out our offsets as we can get to that first. So let's try just increasing Y. We can see as we increase Y, it's as if the audience are looking at an object that's going further and further and further in Y. So let's just keep our attention on these guys, because I think it will be very clear to see as we start increasing and decreasing our Y value.
Very nice.
And what if we were to change our...
For everyone to be able to see this very clearly, take that minimum amp and start bringing it back towards 0, or even go positive slightly.
So we're all stretched out?
Yes, they're all stretched out.
Sure, so I'll just bring our minimum amp to 0. So everyone's stretched out. Oh, this will make it nice and clear. Good call. So yeah, as we start increasing our Y value, everyone leans back and forwards. Now what if we were to increase our X value? X obviously being this direction. Everyone should start to basically face, we can make them face in, we should see them changing their X. Obviously it's very subtle, but you can see that as we move over in negative X, these guys are looking further down because we'd be over here. And this will become more apparent when we move the null, because we actually have a point of reference to look at. And in the Z direction, we should see most effect on this side and this side, as these guys look at something further away and these guys look at something closer. So that would be positive. Obviously, if we go too far, we're underneath and everyone gets very confused, but that's never going to be a situation that we encounter with the final animation.
Nice.
So our offset's working, so let's jump up and grab our null, and I'll grab the move tool. So this should make things a lot clearer, because we can now see... That's pretty cool. So yeah, we can see everyone looking up at this guy and following him around. And once we've got our shader in place, things will become very apparent, because we'll have, you can see their faces, you can see exactly where everybody's looking. Fantastic. So I'm going to set this back down at the origin. And with that, unless there's anything else you'd like to add, that concludes this video.
Done an excellent job. So that's going to wrap things up.
Thank you very much.